So it's one number that's comparable across different studies, and if I give it to you, you can compute the other practical things that matter. There's only one drawback to Cohen's effect size, which is that most people don't really know what it is. If you're in a field where it's widely used, you're familiar with it. If not, it takes a little while to get calibrated. So if I tell you that it's 2, for example, that might not mean anything to you until you look at a picture like this. So that's what it looks like when there's a difference in means of 2 standard deviations. And you can see from that overlap area, you can get a visual representation of the misclassification rate. And for you in your notebook, which is not a given, but this is the other kind of cool tool that I wanted to show you. If you have not used Jupyter before and you have not seen this, you might like having this slider where you can adjust Cohen's effect size. So when it's 2, that's what it looks like. And let's see, when it's like 3, interesting. I'm having the same problem that someone else had, which is, so the way that this is supposed to work is that it updates that figure. But what's happening for me and what might be happening for other people is that instead of making lots and lots of figures, that's too bad. Well, tell you what, instead of interacting, you might find that it's easier to just use this previous cell number 26, and just put in the values here. So let's do that. So with Cohen's effect size of 1, that's whatever. So that's not a super smooth. In fact, there's a lot of overlap. So the misclassification rate here is half of that overlap. The overlap there is the area, and half of that is misclassification. The probability of superiority is now down to 74%. If you are into psychology, differences between members of psychology tend to be like 0.5 or less. And that's what that looks like. So when you see newspaper headlines that talk about these differences between men and women in various cognitive ways, try to find the effect size. And if it's 0.5 or less, you probably don't care. On the other hand, if you see something like 3, you should be somewhat impressed. 3 tells you that basically if you tell me your score on this scale, I can classify you pretty highly. So 3s, 4s, 5s, meaningful, maybe not. Questions? How do we get this? That's a great question. So let's say I tell you it's 2. Yeah, so I'm telling you effect size, and I tell you, okay, I estimated the Cohen effect size of 2. Your natural response is, then it doesn't have much frequency anyway, and we can answer that in the next one. Yes. Yes. I'm treating everything very most of what I'm doing, you could replace distributions with empirical distributions. So just pull random values from an actual sample rather than from a continuous or analytic distribution, and all the problems will be the same. And in fact, we're going to do some of that in the third problem. Other questions? Yes, sir? What would you tell them? Come on, somebody be brave. Yes, sir. 5 times more likely. Okay, that's one way to do it. Other possibilities. 14% is the points. Yeah, so you're just taking the difference between two percentages in percentage points. Yep. So one of those is like an absolute difference in percentage points. That's, I think, a relative probability or ratio of probabilities. Yep. All good. Yes. Who am I representing here? Yes. Who's it? Cui bono? Who benefits? Yes. Who funded the study? Right. Okay. So one possibility is the 14 percentage points. One of the challenges is that you have to figure out which one is the control group and which one is the treatment group. And in this experiment, it's not clear whether withholding peanuts is a treatment or whether administering peanuts is a treatment. And so you could express it in either direction, either plus 14 or minus 14. One difficulty, if you express things in terms of percentage points are not a good way to compare different studies. Because if I tell you that something went from 3% to 17, that might be a really big deal. But if you're like right in the middle of the percentage range from 43 to 57, that might not actually be such a big deal. But if I take some infinitesimally small risk like 0.0001, and I turn it into 14.01 or whatever, I've done you some serious harm. So percentage points are a problem if you're comparing things that are at different range of probability. The other possibilities, you could talk about the percentage decrease. So you could say you will cut the probability of getting allergies by 83% by going from 17 to 4 or 17 to 3. The only problem with that is that now that asymmetry becomes much worse. So now going from 17 to 3 is a reduction of 83%. Going from 3 to 17 is an increase of 467%. So that's kind of awkward. The other thing that's kind of bad is that people get confused when you start talking about percentage differences in percentages. And then you lose your audience. So those are a couple of challenges there. In medicine, the odds ratio is very popular, and this we now have to take our probabilities and express them in terms of odds, and then take a ratio of two pairs of odds. If you are not familiar with odds, it is just another way of expressing a probability. It is equivalent in the sense that if I give you probability, you can compute odds using that formula. If I give you odds, you can compute probability. So it's equivalent in that sense. So here I've got the probabilities 0.03 and 0.17. I can convert them to odds, being those values that you see there, and then the odds ratio is 0.151. Which may not mean a lot to you, but sort of like Cohen's effect size, people who work with odds ratios learn to get calibrated. They have a sense of what that means. And so now you could express this either way. Again, we've got the problem with which direction to go in. I could either say that if you eat the peanuts, you decrease your allergy rate, and the odds ratio is 0.15. Put it the other way around, avoiding peanuts will increase the allergy rate with an odds ratio of 6.6. That's how you're going to see it in medicine most of the time. I'm going to suggest one other possibility, which is the log odds ratio. So take those same numbers that we just had a minute ago, and it's a ratio. You take the log of the ratio, which is the difference between the logs. And one nice thing about it is that it is symmetric. The log odds ratio is 0.82 in this case. Either way, it's just the sign that changes depending on which direction you work in. Now, if I had my magic wand and I could make everybody use log odds ratios, I would. Log odds ratios have a lot of really nice properties. When you are talking about probabilities, they work across the entire range of probabilities. It doesn't matter whether it's tiny, medium, high probability. It's the same information content. And actually, if you want to get into information theory, the log odds ratio is a measure of the information content. It'll tell me what the treatment was. That'll tell me how to do a Bayesian update about how much I should believe you're going to get a peanut allergy. And they add up. If you apply several different treatments that have log odds ratios of 1, 2, and 3, the total of all of those treatments is 6. At least if I assume that they're independent. Yes. Shoot. The problem with log odds ratios is that nobody knows what they are huge, but nobody knows what they are. You have two axolotls. How many other people knew what an axolotl was? All right, they're not quite as obscure. How many people knew about log odds ratios? They're exactly the same. So my analogy is apt. They are. They're very cute. Although I always get confused with an Adelal, which I guess is not good. That's the spear throwing thing. Oh, interesting. Interesting. This is great. We might be off topic, but this is really good. I have only myself to blame. To summarize, there are a lot of different ways to express this. None of them are perfect. There's a little bit of a trade-off here from left to right. The things on the left are problematic from a mathematical point of view, but people understand them. The things on the right are in some sense elegant and mathematical and all that, but for a popular audience, you're not going to get people to understand that. And that's the trade-off that I'm suggesting, is to express effect size, there's probably not one ideal way to do it. You want to choose something that is meaningful in context. You want to choose something that makes sense to your audience, but there's a conflict there. See? I suggest we take a break. Let's resume in 10 minutes, which will be 2:40. If you have questions for me, I'm happy to talk during the break. We should reconvene if everyone's back from the break. I got one question. Actually, several people during the break were asking about this odds ratio and log odds ratio. I was singing their praises about how wonderful they are mathematically, and people were asking, how do I make sense of them? What is my intuition for those things? I will point out, I won't get into this in any depth, but the log odds ratio is the Bayes factor. So if you are familiar with Bayesian statistics or Bayesian update using Bayes rules, the Bayes factor is a measure of the information content. And if you look up the Wikipedia page for Bayes factor, it actually has a table here that was suggested by Jeff Rose. Now you don't have to take this as gospel. Log odds ratio to how strong that effect is. This particular mapping is going to depend on the domain, so I wouldn't take it too seriously, but it's at least a step toward getting calibrated. But that's enough of that for now. Onward to part 2. Okay, so we are going to start talking about quantifying precision. This is the question I got a minute ago. I've measured effect size, and I'm going to tell you that the Cohen effect size is 2, or I'm going to tell you that the log odds ratio is 0.8, and you want to know, how good is my estimate? How much might I be off by? And that is a perfectly good question to ask. So let me start with a different problem, which is that suppose you want to know how heavy people in the United States are, and you decide to do a telephone survey. So you choose random numbers from the phone book, you dial the numbers at random, and whoever answers the phone, you ask them, how much do you weigh? And you write it down, and now we want to try to say something about the U.S. population as a whole based on that way of doing sampling. And my question for all of you is, what could go wrong with that methodology? So talk with a neighbor for a minute and see if you can enumerate all the things that could possibly go wrong. I don't want to interrupt your fun, but I'm going to interrupt your fun. All right, talk to me. What are some things that might be wrong with my methodology? Why is my answer going to be wrong? I hear liars. So people might not tell me the truth. Okay, that's one possibility. Yep. So people who are answering the phone in the middle of the day might not be representative. In what can you think of, like some ways that they might be different? So the numbers are random. I don't necessarily know whether they're at work or at home. Okay. Yep. If I text versus call, why do you think I might get different results if I text or call? Because some people might be in the phone book or not, and that might tell you something about them, whether they're in the phone book or not. Yep. Do they still make phone books? Good. Anything else? Yes, so this is good because you're all telling me two things that are important. One of them is that the people that I get might not be representative, and you're telling me why that might change the answers that I get. Because sometimes you can have a non-representative sample, but it's still okay as long as there's no relationship between the ways that you are unrepresentative and the thing you're trying to measure. Yeah. So people might not be very accurate, maybe because they're lying or maybe just because they don't know exactly. Yep. Yes. Scale might not be calibrated. And it might be related to income, and many of the factors that we listed are related to income. And this is kind of one of the informal rules of social science, is that everything is correlated with income. Person might lie. Yep. Okay, so let me see. I put some ideas in the slides. So one of them, many of you mentioned examples of sampling bias where the sample is not representative. What that means, if the sample is representative, then every person in the population, in this case it's US adults, should have an equal probability of being in the sample. If they have different probabilities depending on what groups they belong to, then that's not a representative sample anymore. And if the thing that you're trying to measure is correlated with that group membership, then the results that you get will be biased. So that's sampling bias. But remember that there are two parts of that. There's a right level of skepticism. No skepticism is bad. Going crazy with skepticism is bad. It's almost impossible to get perfectly representative sampling. It's okay to be approximately representative as long as there's no relationship between group membership and the thing you're trying to measure. Sampling bias, some more examples. People mentioned that people who answer the phone in the middle of the day might be more likely to be unemployed. Whole lot of things that are probably related to income. So you guys mentioned several examples of that. You also mentioned examples of measurement error, uncalibrated scale. Your question is ambiguous about whether you're asking for their weight clothed or unclothed. They might not remember their weight. They might misreport. The value neutral way to talk about lying is that they misreport. You might write it down wrong. Or one of the things that I run into in survey data all the time when I grab survey data is things get miscoded. So I did a study looking at, actually the height data that we looked at came from a very large study, 300,000 respondents. One of the problems with large sample sizes is that gives you more chances to make a mistake. And they had a surprising number of people in that data set who were between 60 and 62 centimeters tall. I think there's only one person in the room right now who might have stepped out who is 60 centimeters. What do you think went wrong? Why were there so many? They were talking feet and inches. I bet there are a lot of people who are 6 feet 0, 6 feet 1. Not so many people, not so many adults. Oh, it could have been 62 inches, which is 5'2". Good point. Yep. The other thing that you see a lot is that missing data will sometimes be encoded as 99 or 999. So I did one study where I looked at birth weights for babies, and the mean came out to about 13 pounds. That can't be right. It's because I had accidentally included a whole bunch of 98 and 99 pound babies, which were respectively don't know and weren't asked or something like that. So measurement error, lots of examples of that. Third thing, so we talked about sampling bias, that's number 1. Measurement error, that's number 2. Number 3, random error, which is just the fact that you collected a sample rather than the whole population. And so if you only call 3 people, then it's pretty clear that you might, just by chance, get 3 heavy people or 3 light people. And your estimate might be off just because of random sampling from the population. So those are the 3 big sources of error: sampling bias, measurement error, and random error. Usually, sampling bias is hard to quantify, often because if you knew what was happening, you would fix it. So you might not know it, and even if you know it, you might not be able to measure it. Measurement error is sometimes quantifiable. There are some ways to do that. For example, if you have 2 different processes, and one of them is more accurate than the other, you can use the difference between them to estimate how imprecise the 2 estimates are, the 2 measurements are. So the second one can be quantified. Third one, random error, turns out to be the easiest one by far to quantify, and therefore it is the one that we spend all of our time in statistics focusing on and completely ignoring the first 2. Despite the fact that in practice, it is almost always the case that those first 2 are much more important than the third one. But the third one is easy, so we do it. That is my warning about everything that I'm about to tell you. I'm not the only one. Edward Tufte agrees with me and managed to express it in 140 characters. Random error is but one of 20 threats to learning from data. It gets disproportionate attention because it is the only threat that can be mathematically modeled. So, let's mathematically model it. Let's get back into the notebooks. If you will open up sampling.py, read through it, run the code, work on the first exercise, and stop when you get to stop here. Okay, we have a fix for the problem that we were having with the interaction. If you find this function called plot sample stats, search for that function, plot sample stats, and add this line at the end, pyplot.show. If you make the show explicit, that should allow you to do the interaction. And now, if you move the slider back and forth, it will update in place. So if you had that problem with interaction, give that a try. Hopefully that solves it. This is in the function that is called plot sample stats. Add this line. I want to go over a couple of things in the notebook. One of them is the distribution of weights for adults in the US is approximately a log normal distribution, which is kind of a funny shape. We're used to things like physical measurements on people and animals. Many, many things have a Gaussian distribution, which is this nice symmetric bell curve. The log normal distribution is not symmetric. It looks like this. It has a long tail on it. So there's sort of a central tendency around 60, 65 kilograms, but then there are heavy people who are up into the 120, 160 kilogram range. Turns out there's a reason for this distribution. At birth, the distribution is pretty close to Gaussian. And then as we become adults, it becomes log normal. If you are curious, I have a footnote in my book which explains why this is true, but it's outside the scope of our current activity. So I'm going to assume temporarily that we know what this distribution is, and I'm going to come back later and undo that assumption. But for now, assuming that we know what the distribution is, we can run simulated experiments that says, what if I took a sample of 100 people and I computed their average weight? And then I took another sample of 100 people and computed their average weight. And I did that experiment over and over. How much would the results differ from one experiment to the next? So that's how we're going to quantify the precision of the estimate, which is by pretending that we did the experiment many times and seeing how different it is from one experiment to the next. Now, the thing about this example that is going to become confusing in a couple of minutes is the difference between n and iters. So n is the sample size, and that's really important. That's the number of people that I'm going to go out and measure. And what we're going to see very soon is that as the sample size gets big, my precision gets better and better. When my sample size is small, no surprise, my precision is not so good. So n is the thing that really matters. Now, to estimate how precise my estimates are, I'm going to run lots and lots of simulated experiments. And I'm calling iters is the number of times I run the experiment. That doesn't matter very much. It just needs to be reasonably big. As long as iters is big enough, I'm going to get a good description of my uncertainty. So iters, I arbitrarily choose 1,000 just because computationally it doesn't take very long and it's big enough that I'm going to get answers that are close enough. Okay? So n is important, that's the sample size. Iters is just the number of simulated experiments that I'm going to do. So there's just taking one sample and computing one sample statistic. And now here, compute sample statistics is the function that runs lots of iterations. And I'm using a Python list comprehension there just as a syntactic way of kind of like a faster for loop in this example. Okay. Now, this distribution is the important part of the whole thing. This is, I ran 100 experiments. No, I ran 1,000 experiments. And for each experiment, I computed the estimated mean of the adult population, and I plotted it. So one time when I ran the experiment, I got 72. And one time when I ran the experiment, I got 74. And then there was that crazy time that I got 68. And that other crazy time that I got 77. And I just plotted them all. And this is showing me how much variability there was from one experiment to the next. Okay? This thing is called the sampling distribution of the mean. It's telling